Greetings everyone and welcome back to the bench. Today on the bench I'm going to talk about the TDA7267 and the TDA7267A audio amplifier ICs. Same die inside, just this one has a larger package. This is the A suffix. And it allows for better heat sinking so it can be operated at higher voltage. But like I say, same die inside, it's the same chip. These are my favorite low power amplifier ICs because, for one thing, at a given supply voltage they give you very good output power. Much better than chips of similar size like the LM380 or the LM386. Another reason why is because all the high numbered pins, or the pins on this side of the chip, are all ground and meant for heat sinking. So when you lay the chip out on a printed circuit board, you can make a large copper area to facilitate heat sinking. And lastly, they don't require a lot of parts. They are fixed gain, but the gain is set up good enough for most audio applications. And because of that, you don't have to worry about feedback parts. And also they've done some other things to reduce the part count. So when I discovered these chips several years ago, probably like 15 years ago, I was delighted to find them. They're so much better than all the older parts. But the bad news is, well, they are now obsolete. In fact, they've been obsolete for probably about 10 years. The good news is, you can still find them. There's so many of them made. They're widely available. You can't find them at the regular places like DigiKey or Mouser. But you can find new old stock on eBay, still at reasonable prices. Now I'm not sure if these have been counterfeited or not. With these lower power chips, the die are so small that it doesn't make that much sense to counterfeit. And you know, I bought some back in the day from DigiKey, and later on I bought some from eBay, and all the parts were authentic. One check I think you could do to validate your chip is to look at the pins. They used thicker pins on these chips because, like I say, you know, the upper row is for heat sinking, and these are tinned copper, and they used a lot thicker gauge than they would on something like an LM386 or LM380. And when they counterfeit these parts, because of the price of copper, I can see them using a thinner gauge. And of course, you can run tests and see if you're getting similar results that I do when I do the power test to see if it's an authentic part. But like I say, I'm not convinced that they counterfeited these things, though, you know, they can counterfeit anything. Let's take a squiz at the datasheet here. Gonna ignore the power ratings. They always rate these at 10%. But being a single-ended type output as opposed to bridged, it does a pretty good job. They call it a new technology because of the way they designed it, where it doesn't need a lot of parts. You know, it doesn't need a bootstrap circuit, yet it can still deliver decent output power. And the basic circuit, as you can see, doesn't require hardly any parts, though to be done right, in my book, it has to have the RF filter on the input and some absolute maximum parameters. Here's where I was mentioning all these pins are meant for heat sinking, and they're showing you the copper foil area on the heat sink, where you can design that for heat dissipation. Some parameters here. Typical value of 100 kilo ohms input impedance. It does have a standby circuit you can use by grounding the SVR pin. So you can just ignore that if you don't want to have it. So that's kind of nice how they set that up. They give you a sample circuit layout. And we get in the curves here. And it has pretty respectable distortion values for 1 kilohertz. You can see it dives below 0.1%. Of course, at higher frequencies, you know, any solid state amp will have more distortion relatively, but yeah, it's not too bad. So you can see it. What are they doing there? 15 kilohertz. You can see it's higher, but it's still well under 1%. Okay, here's the board layout I've come up with. Nice and compact. This is the heat sink foil area, and this would vary in size depending on how you're going to use the chip, depending on the supply voltage and the load impedance. You can use the graph on the datasheet to help calculate this. Yeah, this could be larger or smaller. In fact, at lower voltages you may not even need it. You know, for example, 9 volts 8 ohms, you don't even really need a heat sink. Pin 6 here is the signal ground or small signal ground. It must be connected to the power ground or the heatsink side for the chip to work. However, you can use that pin to return your input ground. An SVR pin, you know, goes to the capacitor, can connect to that ground as well. Those are small signals and must be isolated from the output return and power ground. So that pin makes it easier to do. It's kind of like a star ground type arrangement. And here's the schematic diagram. It has 3 extra parts that are not shown on the data sheet, and I've changed the value of some parts to make it better, I think. So the extra parts I added is this resistor and this capacitor here. That's part of a low pass filter that blocks high frequencies and RF from getting into the amplifier. It's well beyond the audio range, but it helps prevent the amplifier from receiving RF and even oscillating when the input pin is left open. I also added a small film or ceramic capacitor to help decouple the supply. I'm using a 2200 microfarad capacitor on the output. So when you're using a lower impedance load like 4 ohms, you'll get better bass response. Now for hi-fi, this could stand to be much larger, but it becomes not really practical on these smaller low power chips. I also increased the value of the input to improve the low frequency response. However, the value of this capacitor causes the bass to roll off earlier than it would with this value, so I just put that in as good design practice. You can use a 0.1 if you want and use a 1000 microfarad here if you're not too concerned about low bass response. And of course, all this is small signal ground here. You want all these parts to return to this ground using pin 6, but pin 6 here is bonded to pins 9 through 16, which are the power or heatsink side of the chip. Okay, here's the board. And some copper here. Just soldered on a little heatsink. Yeah, it's good enough for this test. It might need to be larger though. But yeah, just made this board for the video. So got it all hooked up, and we'll give you a little music sample. Okay, let's play some YouTube safe Muzak. Sounds pretty good. There's a very light hiss. Amplifier does have quite a bit of gain. It is good enough for music players. No problem, you know, turning up the music player, reaching the amplifier's limits. That's one thing I noticed with some amplifier boards. They don't have enough gain, but this one has plenty of gain. Okay, let's do this. Power measurement time. So I hooked up the non-inductive 8 ohm load. Use the preamp because it has a volume control. Whereas the stepping action of this one, you know, it's just too coarse. Each step changes it too much. But with the preamp, I can fine tune it. So get you pointed here at the oscilloscope. Get some measurements. We're measuring at 12-volt supply. What I'll do is take one measurement on camera, and then I'll do a bunch more and regurgitate those at the end of the video. Okay, here we go. There's clipping. Clipping looks good. I don't see any oscillations or any weirdness to it. It does start to clip on the top side first, though. Not perfectly symmetrical. So we'll just tune that flat spot out. Looks like 3.47. And oh my, what's going on here? Must have left it on. The VFD calculator is not working. Have to try some batteries for that. Anyway, what did I say initially? 3.47, 3.47 squared. That's RMS measurement, of course. Divided that by 8 ohms. 1.5. That's pretty good for the voltage. 8 ohm load. 1.5 watts. Okay, so like I said, I'll take some more measurements and report at the end of the video. Man, we're lit up like a Christmas tree. We've got all the equipment going here. So we're going to do a frequency response test using the Outtakes arbitrary waveform generator. So let's get the camera on the oscilloscope here. So this tip should be touching this graticule, so I set that up. We're at 1 kilohertz. And this tip, I guess I should be more technical and call it a peak. This peak is at this graticule, and this peak at this graticule at 0 dB. Okay, let's get this going here. So we'll crank this thing down to something small like 10 hertz. Okay, we'll start at 10 hertz, and obviously the signal is way down, you know, a little below half. That's due to the output coupling capacitor. It's kind of impractical to use a very large value one. I'm using a 2200 microfarad, and I do have a 4 ohm load. I'm testing it at 4 ohms. So yeah, it's going to roll off the bass quite a bit. See, here's 20. It's not too bad. It's a bit above 66%. We'll go ahead and crank it up. Pretty much there at around 60 hertz. So it'll stay there all the way up to 20 kilohertz, I would expect. Let me crank this up. Yeah, we're picking up some sort of noise. See, at some frequencies it's in sync. It must be from the Outtakes. I don't know. I didn't see that before. And there you go, 20 hertz, or I'm sorry, 20 kilohertz, and it's flat. Oh, like I always do, we'll crank it up higher, and it's starting to roll off a little bit, around 35 kilohertz. So frequency response is pretty decent with this, except for, like I say, the low end where the output coupling capacitor rolls off your response. That's why they go direct couple with hi-fi amplifiers, because you know, with 8 or 4 ohm speakers, it takes a very large value capacitor to keep that response flat down to 20 hertz. Okay, we're going to take a look at distortion. Let me tune that out. This is the 1 kilohertz fundamental, 4.5 kilohertz, 1% pilot signal. As I always say, I just put that in the signal so I can see how the little other harmonic nodes relate to that in height. Lets me know how much other distortion there is. So, okay, here's clipping. So we'll tune that out till the little nodes are gone. It's right at clipping. We're looking at a very nice amplifier. I am measuring at 4 ohms. I'm giving this thing a bit of a challenge, and it's doing pretty good for a low power cheapo chip amp. Okay, we're now at 10 kilohertz. Tune out the clipping. And we're getting some small nodes. I don't have a pilot signal in my 10 kilohertz signal, but there are some small nodes. It will be harder for a solid state amplifier to deliver low distortion into a higher frequency. Okay, now we're at 20 hertz, and let me dial back. There we go. Dial back the clipping, and it's pretty clean. There's a little notch of a second harmonic, but other than that, it's pretty clean. Not bad at all with a 4 ohm load for this type of chip amp. Okay, so here are the power measurement results. I'm not going to read all of them off, but I measured common battery voltages from 6 all the way up to 15 volts. Well, these aren't really common battery voltages, but wanted to get the top end. The amplifier can handle up to 18 volts, though I really would stop at 15. With 4 ohm loads, I wouldn't go over 12 volts because the amplifier has a peak current of 1.5 amps, and you're starting to push it around 12 volts. I noticed the waveform was starting to look a little distressed, a little distorted when I was getting up in the 14 and 15 volt range with a 4 ohm load, telling me that the current limit or maybe a drive issue with the output stage was coming into effect there. But pretty impressive numbers at 8 ohm loads. While it can't really swing all the way to the rails, the output voltage can't swing all the way to the rails, it's doing pretty well. Has a really nice optimized output stage for doing that without using a bootstrap circuit or anything like that. Pretty nice numbers with 4 ohm loads as well, but not quite as nice as something like the TDA7267A where it does really well with lower impedance loads. But really impressive amplifier for what it is. Idle current draw was 16 milliamps, so I would consider that battery friendly. It's not like the LM386, which I don't remember its numbers, but I think it's less than 10 milliamps. But you know, this is under 25 milliamps, so pretty battery friendly. And to summarize some of the other things, frequency response is exactly as expected. Roll off due to the output coupling capacitor, but beyond that, it's flat all the way out to and beyond 20 kilohertz. Has a slight amount of noise or hiss in the background. That's because the amplifier does have quite a bit of gain, but I would take that because it has no problem with headphone type output music sources, whereas some amplifiers, they don't get that loud when you turn the music source all the way up because they just don't have enough gain. So very good there. Distortion from such a chip amp with 4 ohm loads is excellent. Maybe it's not hi-fi, but it's still pretty good. All in all, you can see why this is my favorite low-power chip amp, and I would highly recommend them. It's really a shame they stopped making them, but like I said, you can certainly find them. Well, that's going to do it for this one. Thanks for watching. I have an old radio here. Behind it is some CDs and an old video game. But sandwiched in between is the Snickers. The sleeping Snickers. Huh? What? Really?